Hello to everyone who's just joined us, and once again, welcome to October's Stats Toolbox. Today we have Jasper Slingsby. Jasper is a lecturer at the Biological Sciences Department at UCT. He's also a research associate at SEON. Jasper will be talking to today about ecological forecasting in GIS and R. Over to you, Jasper.
Thanks, Craig. Okay, so as I said in the abstract, I'm doing a bit of a cheapskate maneuver, and I'm just kind of advertising some of the teaching resources I've been developing since I've joined UCT. The SEEC Toolbox veterans among you will be familiar with me talking about spatial data analysis in R in previous years, and I've got these three kind of tutorials on my blog that I was updating every year, but I didn't update it last year. And when I started teaching at UCT, I was asked to teach a week's module of GIS to the honors class. So I started afresh rather than just updating these. I shifted to the book down format and developed this resource, which I just thought I'd show to you quickly. And then I've also developed a similar resource for a third-year course where I was teaching a module on ecological forecasting. I'm getting feedback from someone. I don't know if it's Craig or somebody else. If you could just turn your mic off. Yeah. So the thing with the old R tutorials that are on my blog is that a lot of the kind of best packages to use and that kind of thing have changed. And I also didn't really provide a proper introduction to GIS in them. So the new resource, quite a bit of it is just the basics. What is GIS? How do we do GIS? And then at least in a UCT context, how you can get help in terms of contacting the GIS help desk and that kind of thing. And then the basics of things like data formats, vector versus raster, attribute data linked to different file types, and then the various different file formats. So just some kind of basic notes on the general bits and pieces that you need to know when doing GIS. And then a couple of the more important concepts and pitfalls like scale and coordinate reference systems. I'm not going to go through them in this talk just because this is a week-long module. It probably wouldn't take you more than a couple of hours to read through the whole thing. But yeah, these first kind of 5 chapters are more around the basics of GIS, and then from chapters 6 to 8 are about R as a GIS. So a kind of a general overview about the different major task views and extension packages that do GIS or can be used to do GIS in R, and then just a discussion of some of the key packages. So in the past, I was predominantly using SP and RGDAL for handling vector data for polygons, lines, and points. But now the kind of new fancy package is this package called SF, Simple Features for R. And SP is going to be it's now sunset software, and that it's going to be discontinued. So it's not going to be supported in the long term. So moving to SF is a good option. SF is great. It's incredibly powerful. It's very blends nicely with a tidyverse way of coding, so you can use pipe operators and that kind of thing. But it also is in compliance with the Open Geospatial Consortium Simple Feature Standard, which is a major plus. And it can handle almost any kind of vector data. So that's quite nice. And so I do chapter 7 here as kind of vector GIS operations in R, predominantly using SF. There's a few things where I went back to using library SP functions just because it was simpler, or SF might not have a feature for that yet. But every year SF is getting better and better. So I will be updating this tutorial every year and probably adding and improving this kind of demonstration set. Yeah, just a list of the functions from SF, and there's a nice cheat sheet that tells you how to do different things. It is unfortunately one of these packages where they decided to name all the functions with a prefix. So they're almost all st underscore and then the function, which is incredibly unhelpful if you want to use R help, because everything is under S. But it is what it is. And yeah, generally I find the help functions or the help documentation for SF isn't great. But if you Google it, you'll find good answers. And then the other, for the raster data, I stuck with using the package raster because that was the way I knew how, and I was running out of time in terms of teaching the honors class. But just to let you know that there's a new package out called Terra, which is also being developed by Robert Hymans, and it's meant to replace raster entirely. So raster is also becoming the sunset software, and that it's not going to be continued. It is for probably for the next couple of years, but generally Bavand and Robert Hymans, sorry, is moving to supporting Terra and not really supporting raster anymore. This little quote from Roger Bavand: Terra is very similar to the raster package, but Terra is simpler, better, and faster. You know, standard bank type clause. But it really is, and a lot of the functions are actually just the same, but some of them they've changed the names and that kind of thing. But it is way more efficient than using raster. So the tutorial at this stage still uses the raster package, but next year I'll update it to use the Terra package because I've been moving over to that. So that's the general basics of this. I do a case study using data sets from the Cape Peninsula, all open source data sets you can download from the links here, although I do notice that the links are broken, so I need to fix them, apologies. I'll try and do that after this. And then, yeah, and it's essentially just a case study using the Cape Peninsula, using the veg types, water courses, species localities from iNaturalist, and an elevation data set. And then kind of I go work through all the basics, reading and writing, cropping, plotting, all that kind of thing. So I think this would be, I feel like this is a nicer resource than the old one, but there are definitely things in the old one that I haven't brought into this one yet. So I'll do that in the next revision, which will be early next year. The other resource that I wanted to tell you about is from a third-year course that I just taught on a basic introduction to ecological forecasting. It is, for some of you, it might be too simplistic because it is focused on kind of third-year level, but at the same time, it is kind of a nice soft introduction. A lot of the context for this was from a paper and a book by Michael Dietzer. So let me just find the resources. Yeah, so here there's this book, Ecological Forecasting by Michael Dietzer, 2017, and there's also a great paper in PNAS, Iterative Near-Term Ecological Forecasting Needs, Opportunities, and Challenges. And they really frame what I've done for this course. Obviously, I brought in lots of other bits and pieces, but that's, if you want a quick primer that's not reading through this resource I've made, then those are great places to go to. Particularly this PNAS paper, it's a very nice read. And yeah, and essentially there's a bit of a trade-off between it being broken down as lecture content versus notes that people can dip into and use. But I hope that I have broken it into components that make sense. So the first is just kind of like an overview of a course. So you probably don't need to read that other than maybe, no, you probably don't need to read that, to be honest. Then there was a practical, and there's a preparation step for the practical. You might want to try the practical. It's a lesson in using, doing pair coding using GitHub. So if you're not using GitHub, then yeah, by all means, have a dip and see if it works for you. And then, yeah, just a general introduction to the concept of models and decision making, and how we generally make decisions, but then how we can get quantitative in informing the ways we make decisions, and ultimately getting to the idea of iterative near-term ecological forecasting. So some of the kind of main principles here is that currently most of the forecasting we do is for too far into the future to actually assess how well we did. You know, most of the kind of species distribution model style climate change vulnerability assessments are, you know, into projections 50 years into the future. and for some of us at least, we'll be retired by then, and so no one can really question how well we did in our forecasts. But the idea with iterative near-term ecological forecasting is to make those forecasts near-term and make them on a time scale that we can actually assess how well we did and learn from that. And so the key here is both making it near-term, making it near-term so that it can be iterative. Previously we kind of just fit our model with whatever data we can find and then make a projection and walk away, and maybe say to some policymakers, oh yeah, you should worry about this. But actually there's very little basis for them to assess the validity of the work we've done. So making them near-term forecasts and being able to learn from how well our forecasts do relative to reality really is a great advantage. And it then becomes an iterative cycle, which is a learning cycle, which kind of mirrors the scientific method. So I'm not going to describe this whole process of, initial conditions, make a forecast. So here's your initial conditions, your forecast, and here are now your new observations at the time that you projected to or forecast to. And so now you need to come up with a new kind of estimate of the initial conditions, which now might be the pink, and then you make your next forecast in the time state. That might be too quick. But the idea here is that you're following a cycle that mirrors the scientific method to some degree, in that we kind of form hypotheses, make predictions, test those hypotheses, and interpret the results. In the iterative forecasting cycle, that would be kind of you develop your forecast, make your forecast from your initial conditions or your current state, which is the blue. You make your forecast. You then collect new observations, which is your pink here, and you compare that to the observed state, and you compare your forecast to the observed state. You use that to kind of develop your new estimate of the current conditions for your next forecast. So it follows this kind of iterative process, and a very nice thing about this is that it blends well with both the scientific method cycle, but also with adaptive management and adaptive monitoring. So here's your iterative forecasting cycle. You kind of measure your initial conditions, you develop your model, you use that to make a forecast for the next time step. So from your initial conditions to the next time step. And then you collect new data and compare your forecasts and your observations, and then repeat. That's your iterative forecast cycle. In an adaptive management cycle, you usually kind of identify a problem and assess and evaluate that problem. You generate alternatives in terms of decisions and potential outcomes. At this stage, you would then try and set up mental models about how to integrate that information and consider trade-offs. But the nice thing about having ecological forecasting is that you can actually formalize that and use those alternatives as scenarios to plug into your forecasting, into your model for your forecasts. And then you can feed that information back into the step of actually assessing the trade-offs. So rather than kind of having a thumbsuck of what the alternatives may be and what the outcomes might be, you can actually then formalize that into a model and get kind of quantitative estimates. The next step would then in the adaptive management cycle is then making a decision and then monitoring the outcomes. And this is where the forecasting cycle can be useful as well, because you can actually inform that monitoring. So based on how well the forecasting model is doing and propagating and partitioning your uncertainty in that model, you can then identify, well, what are the data that we need to improve the model? So rather than just monitoring only the outcome, maybe we need to monitor some other components that allow us to predict that outcome as well. And so these two cycles blend together in two nice ways, in that there's the scenarios that inform the scenarios that you provide your forecasts for, that can be fed back into the adaptive management cycle, but then also you can inform the actual monitoring. And this is essentially another cycle altogether, the adaptive monitoring cycle, which is in another paper by Linden, Meyer, and Likens. And And then obviously from the monitoring, you then get your kind of new observations that can feed into your next forecast cycle. So it's a really nice framework. Obviously, it's not suited to every possible problem out there. It works very nicely if there's already an adaptive management system in place and people have their alternatives and the potential issues and the potential trade-offs, and you as a modeler can step in and be like, hey, maybe I can develop a model for that and try and give you quantitative estimates of the outcomes. So it's a nice framework to feed into this adaptive management cycle. If you don't have the adaptive management cycle in place, then obviously it becomes far more complex, and that you need to do a lot of kind of stakeholder engagement and working out what it is you need to forecast and how to provide it in a useful way. So that's kind of the general basics of the iterative forecast cycle. The other main component is that in doing iterations, you can start with a model that's probably not very good. And then through each iteration, you improve the model. You can learn by doing is the idea. And rather than following the kind of traditional ecologist's approach of, we've done 60 years of studies and experiments, and maybe we're ready to start, creating models that can produce forecasts. The argument put forward by Dietze and others is that we need to adopt more of an engineering view of it and be like, well, we're going to have to make a decision anyway with whatever information we have. So we may as well start modeling. And in starting that modeling process, we'll start to identify the problems with the model and what we need to do to improve it. And so we'll ramp up and get better much faster. And that's kind of the approach that weather forecasting took. Early weather forecasts were relatively useless, and they kind of have a bit of a bad rep, but even in the last 10 years, they've got way better. I think most of us are avid believers in Yono or some of the other weather sites, and that's because their forecasts have actually become really good. They do seem to overpredict rainfall, but I think they just can't believe that it doesn't rain in countries other than Norway. So there you have it. And then just to highlight that two very important components of ecological forecasting are basing the model on solid data management and preferably reproducible research, because that allows for kind of an efficient informatics pipeline. So if you really want to be sharing everything you're doing, you want others to be able to use it, you want others to be able to repeat your model very easily and that kind of thing. So there's a big focus on using reproducible research principles, and then obviously with good data management, that includes things like the data life cycle and the like. And so I've kind of adapted the figure I was explaining earlier, this figure here, to this kind of Olympian challenge of data-driven ecological decision-making, where before we had adaptive management, ecological forecasting, adaptive monitoring, and the scientific method, but you add this ring of reproducible research, which includes data management. So in terms of the rest of the online material, I provide some examples looking at proteodemography and with both the kind of management need and some studies that are getting close to being useful ecological forecasts. And then two sections on, one on reproducible research and going through everything from the argument as to why we need reproducible research through to some of the tools and tricks to get there, and a lot of kind of like motivation as to why we should be working reproducibly. So I think this is probably a useful read to many, even those who are sold by the idea but don't actually quite practice it. I'm trying more and more to work reproducibly. I'm not quite there yet, but with each day I try and get a little bit closer. So this is, and then there's a chapter on the practical that I mentioned earlier, and then a section on data management, which essentially just goes through like why you need to manage your data well, what the issues are with not managing your data well, and then the data life cycle, discussing everything from planning through analyzing your data. And then the rest is really kind of like soft intro to some of the nuts and bolts of ecological forecasting. I give a basic introduction to Bayesian statistics, because that's kind of the preferred method to use when doing ecological forecasting, because it has several advantages, one of which is that you can just feed new data into the model, into the existing model, as new observations, and you can use your previous forecast as a prior in that model. So you can literally use, the Bayesian framework provides a nice kind of iterative and probabilistic framework within which to do this kind of iterative forecasting. But there's many other advantages as well that I go into in this online material. I should say that I probably have taken liberties at this stage. So if any of you do go through this and you spot errors or things that you don't agree with, by all means contact me, or even feel free to send a GitHub pull request or something like that. Because I really do want to make this as good as possible, but at the same time, my training is all in ecology. I've never actually done any formal training in Bayesian statistics, so I probably have made some errors. So that's worth putting out there, that any feedback is very welcome. I also go through the concept of data fusion, which is kind of the idea I was just saying, where the benefits of using a Bayesian model are that you can, well, there's quite a few. Oh, hang on. This isn't the one. This is a different one. Sorry. Yeah, just the benefits of going Bayesian that allows you to do, I know you can do hierarchical models with frequentist approaches, but generally it seems to be easier to do in a Bayesian framework, and that really allows you to pull in varied data sources and data types that you can put in to the model in different weird and wonderful ways. And then a long section on uncertainty, propagating and reducing uncertainty, and kind of identifying the sources of uncertainty and how to improve the proficiency of your model. So the general forecast proficiency is a combination of how good your model is and how far into the future you need to be able to forecast to be useful to the decision maker. And so you end up with this kind of forecast proficiency threshold or event horizon that has a kind of an average and a lower and upper estimate based on the uncertainty in your model. And so this is all about trying to look at sources and types of uncertainty and how to improve your forecast proficiency. And then, yeah, last is kind of completing the data forecast cycle. So that's the data assimilation step. And that's where you're feeding things back into Bayes' theorem. So this is kind of the idea here. So you would start at time 0. You have your kind of initial data, your initial conditions. You have your initial set of priors, which you've obtained independently to your data. You use that to kind of develop a forecast, which is your posterior, and that's your forecast for time 0 + 1. But it also feeds into your next iteration of the model as the prior. Then you add new observations, develop a new forecast, which is now your new posterior, and then so on and so forth. Yeah, so I've covered a lot in a very short period of time, but this is a 2-week lecture module. So I thought I'd just give you a quick skim over the top, but just to make you aware that it's a resource that's out there should you be interested. And I thought I'd just include this as an add-on to the kind of GIS one, which is my usual SEEC Stats Toolbox. I think at this stage, I'll open the floor to questions. Anyone? Lindsay.
Thanks, Jasper. I wanted to ask, the iterative process, how would it cope with a shock, like a big drought or, some kind of event that wasn't built into the adaptive management framework in the first place?
No, that is a big issue. So that comes in 2 places, and I suppose one answer is that it doesn't deal with it. The other answer is that it's the kind of thing that one would hope you would include in your scenarios. So if you, sorry, I'm getting Daniel, can you? Yeah, thank you. So it's something that you would hope to include in your scenarios, but obviously you may well not have thought to include that in your scenarios because it's a shock that you didn't think of. But there's this section, sorry, I've now opened all the chat windows and participant windows and they're in the way. There's this section on the different sources of uncertainty. And essentially your predictive variance is dependent on like various factors, which is kind of the uncertainty in each of the components multiplied by the sensitivity of your prediction to them. But a big component is the kind of process error, which includes just general stochasticity. And that's something that's very, very, very difficult to reduce. So as you say, yeah, you're very likely to end out having made some or other forecast, but then there's a big shock that no one was anticipating, and all of a sudden your forecast is relatively useless. And so the hope is that either you would have saw that coming and had a scenario for that, or alternatively, you will now have a scenario for that next time. But yeah, it is a big problem. And also just there are some things that will not be predictable.
Yeah, exactly. I mean, we're working with a lot of uncertainty, but then we know extreme events are becoming more frequent. So I guess you have a scenario with and without an extreme event in it.
Yeah.
Well, yeah. Okay. Yeah. Thanks very much. Thanks. It was really interesting.
I think, yeah, I mean, another thing is also just to question, you know, even if you are in a landscape where extreme events happen, it's just a question, well, how useful is it to know what should be happening without that extreme event? So in a feinboss scenario, you know, we know it's going to burn sooner or later, but we don't know when. And if you're trying to make a forecast without fire, they can still be useful. But you also know, you also make the forecast well aware that the utility of your forecast may reduce to zero very quickly in some summer afternoon.
Yeah. Okay. Thank you. Thanks.
Yeah. I'm sorry, I'm just getting my participants list up. Any other questions? Rez.
Yeah, Jasper, thank you very much. That was a really interesting toolbox. And I definitely need to read your notes. I've looked at them a little bit, but I need to read them carefully. I just quickly wanted to ask, so the forecast horizon, how far into the future do you think is it like typically possible to predict in ecological problems?
Well, yeah, so that's yeah, I mean, that in itself is a very interesting question. It really depends on what you're trying to forecast. So the framework is flexible for anything from, you know, days through to decades. But then obviously the question is whether or not you can make a useful forecast of that length or distance into the future. And I think that's where the kind of idea of the trick is to start modeling and then slowly improve, you know, because you may well start with your model is way below the kind of forecast proficiency threshold required to actually be useful to a decision maker. But if you keep working at it, hopefully you can raise it above this line and then be able to forecast further and further into the future. Was that a slippery politician?
No, thanks. No, I was just thinking sort of what your experience is in, like, typically. Well, I know for feinboss, I think some of your models can forecast quite far into the future, actually. If it's,
Yeah, so it's an interesting one. So the post-fire recovery model that we've been working with in feinboss, it doesn't really qualify as a proper ecological forecast in the way that it's framed in Dietze and others' kind of approach to this. You know, I think they typically have state space models in mind rather than you know, what we've done is we've said, you know, this is what a post-fire recovery profile should look like. And once we fit that once, the model seems amazingly good at predicting very far into the future. So at the moment we're using, you know, we've been fitting the model on data from 2000 to mid-2014, and we've been making projections that are useful to today. So yeah, it'll vary a lot, but it's kind of interesting in that we've taken a very different approach in that it's not iterative. It's not a state space model. but it's still useful. So I take a more flexible approach to what ecological forecasting should be, but I also see the value in trying to make it iterative so that you're forced to evaluate it and improve it more frequently. So we've been thinking about how to try and change our model to be more, well, to see if we can rebuild it in a state-space framework, even if it's informed by our kind of more static process model, I suppose.
Thanks.
And that said, also, yeah, you know, we've been using it, fitting it to mid-2014 because that's before the drought happened, which was an extreme event. And it'll be interesting to see if it remains useful going forward now that we've had that extreme event. You know, do things bounce back, or do we now need to refit the model to take into account that this biggest extreme event has happened? Tim.
Hi, Jasper. Thank you for that. I found your introduction to GIS and R really useful. A few weeks ago, someone sent it to me, and it's been really helpful. So thanks for that. And also the Robin Lovelace tutorial you linked to was great. My question with regards to forecasting is just what has it mostly been used for? Has it been climate change, land use change, invasive species, or like exploitation of species, like harvesting? What is it most amenable to? Because I'm kind of thinking land use change is something I might be interested to look into, but is that much more difficult than forecasting the effect of climate changes, or not necessarily?
Let me try and find the website for you, sorry. So there's an Ecological Forecasting Initiative webpage, and they've got a bunch of examples. And it's a bit of everything, you know. So something like fish stocks is probably a pretty good example of an existing kind of framework for ecological forecasting that's quite common or commonly used out there. So these kind of like population demography type models, but then also in the book they have a bunch of different examples, including kind of biogeochemical processes and you know, carbon cycle. Yeah, really, it's amenable to almost any ecological problem. It's just about thinking about how you would frame it. And there is a land use change example. I just need to. Website's not that useful. It's not that. Yeah, I don't want to go digging in the website now. There's a lot of content, and I feel like I can never find the thing that I remember seeing yesterday. But somewhere in there, there's a set of different examples, and there was an interesting land use change one, or land cover change one from Brazil, for example, that I've been wanting to look at more closely and think about in the South African context. But yeah, really, kind of almost any ecological problem that has, I suppose, a time series component, which is almost any ecological problem.
Cool, thanks. I'll have a look at the website.
Yeah. Cool. No more takers? Last chance before Craig lets me go. Cool. Take it away, Craig.
Yeah, I don't think there are any more questions. Alternatively, if something pops up, you can email Jasper directly. Jasper, is that cool?
Yeah, that's sure. That's completely cool. Jasper.Slingsby at uct.ac.za. Yeah.
Cool. So if there aren't any more questions, thank you very much for joining us. And thank you very much, Jasper, for the toolbox talk. And we should have another toolbox talk lined up for the month of November. So look out for that invite. So I'm going to stop this meeting, this recording now. And once again, thank you. Thanks, everyone.
Cool. Thanks all. Thanks, Craig. See you all soon.
Yes.
Cheers.